I will move on to the next topic under modern topics in stochastic processes as we look at Markov decision processes. Okay, MDPs. Um, a decision process. MDP is a mathematical framework for modeling sequential decision making under uncertainty, and it is defined by the Markov property. So you see, every all this still plays into the whole idea of Markov, right? That if you have the probability that S of t plus one given st, at, st minus one, and all that is simply equal to probability S of t plus one given S of t, a of t. S sub t, a sub t. Every other thing before t is not necessary. So to determine what happens at t plus 1, the state at t plus 1, it is determined by the state at t and the action taken at a step before it, like ST, AT, like that. So of course you can see state as so state is the condition of whatever you're observing at time t, but for t plus 1 it is at the next step, and A is the action at t that led to that next state. So this means the future depends only on the present state and action, and that is the Markov property, which we saw very since early on in the playlist. So an MDP is defined as a tuple S, comma A, comma P, comma R, comma gamma, where S is the set of states. So, I mean, whatever it is you are observing, then A is the set of actions. Which actions are you taking that are resulting to the states? Then probability S prime given S, comma A is the transition probability. Probability that when you take a particular action at a particular state, you're going to get to another state, S prime. That's the transition probability. Then R S comma A is the reward function. All right. I think there was we at some point we looked at the reward renewal process, right? That when you take a particular action at a particular state, it's at a reward is attached to it. And as we're going to see probably in the next video, in a video after now, we're going to be looking at the idea of reinforcement learning. And this is the basic idea of reinforcement learning, right? Like you have a situation where if you do a particular action, you get some points for it, or if you do otherwise you lose some points. So the system then is optimized in such a way that it wants to take the positive, the beneficial step as much as possible, right? So that's the basic idea of reinforcement learning, and we have that a lot in gaming. Okay, then you then have gamma, which is an element of the closed interval 0, 1, and it's the discount factor. So the intuition here is that an agent observes some states and takes an action and receives reward and then moves to the next state. That's the basic thing about that. And this is also a perfect description of reinforcement learning in machine learning. So, and then we talk about policies, right? So a policy defines how the agent chooses actions. Now, if you look, I have a playlist on machine learning, or if you like data science, and I got to talk about things like supervised learning, non-supervised learning, and reinforcement learning. So the idea of policy comes up there a lot because you are going to whatever the evolution of the system is going to be dependent on state actions and rewards. So a policy defines how the agent chooses actions. So there's a deterministic policy which says pi of s is equal to a. So the pi of a given state is equal to the action, right? Then you have the stochastic policy, which is probabilistic, right? Which says probability that you take a particular action given that you're in a particular state. For instance, what action are you likely going to take if you are feeling hungry? What would you do? Would you just drink water, or would you just go and sleep? I know people for whom sleep is stronger than hunger. For me, if I'm hungry, I can't sleep. So, you want to determine what works for you in that case. So that's just an example of a stochastic policy. What's the probability? So the pi of taking a particular action given that you're in a particular state S. Then that talks about policy. So you have deterministic and stochastic policies. Then you have value functions. So you have a state value function. You have v pi of s, which is the expected sub pi of summation from t equals 0 to infinity of gamma raised power t rt given s naught equals s. And then you have the action value function. So it's all about state and action, state action reward, state action reward, like that. And you have discount policies, like you have so the discount factor, right? So for whatever you do, you are going to gets some benefit or penalty, right? So for action, you have q pi of s comma a is expected value, expected pi. So that pi is the function that is driving the system of summation from t equals 0 to infinity of gamma raised by t r of t, given that s not equals s and a not equals a. Okay, so given that you have taken an action, an initial action a, and at a initial state s, so um, you have this now, the expected value that you have this, given that you've done all of that. That's the action value function. And then we have the Bellman equations. Bellman equation, expectation equation is this, I mean, it's all about action and states and shifting states and everything. So you have V pi of S to be summation over A of, summation over the actions, right? Of pi A given S, summation over S prime, probability S prime given S comma A. That's a probability that you move to a new state given the that you're in a particular state and you took an action at that state, and then all of that multiplied by the reward at state S with action A plus the discount factor multiplied by V pi S prime. That's talking about the new state now. So you have Bellman optimality equation. So you have V star S, which is maximum over A of summation S prime, probability S prime given S A, and then all of that multiplied by the reward, with for action A at state S plus discount factor multiplied by V star S prime. Okay, so we have an example set up here to consider. We consider a simple Markov decision process. Imagine you have states S 0 and 1, and you have actions A 0 and 1, and there's a discount factor gamma 0.9. So the transition probabilities can then be like this. That probability that you move to state 0, given that you took you're at state 0 and you took action 0. Let's say that is 0.8. Then probability that you move to state 1, given that you're at state 0 and you took action 0 is 0.2. Probability you're at state 0, given that you move to state 0, right? Given that you're at state 0 and you took action 1, that's 0.5. So probability you move to state 1, given that you were at state 0 and you took action 1, that's also 0.5. And then we have the probability that you're at state 1 and you remain at state 1, given any action at all, that is 1. So that's like what's that thing called? And that's like a trap. There's a special word it is called. It's like a place where you get stuck, kind of, because there's a guarantee that you get into that state without leaving. Then you have rewards now. Our reward for state 0 action 0, that's 5. Reward for state 0 action 1, that's 10. Reward for action state 1 action 0 minus 1. Reward for state 1 action 1, that's 2. Like that. So that's a very good setup of the kind of thing we're talking about. Then we can, try to, so first of all, we set up all these things now. So for 0 and 1, for the state and actions, right? As you can see, so for state 0, we have 0.8, 0.2, and for, so moving from 0 to 0 now is like 0.8, 0.2. Moving from 0 to 1, now you have 0.5, 0.5. Moving from 1 to 0, you have 0, 0, 0, 1.0. Then moving from 1 to 1, that's like you're at 1, you know. So you have 0, 0, 1.0. Like, so moving from 1 to 1, that's what we have here now. So it's always guaranteed that you're moving from 1 to 1. That's 1.0, like that. And for the reward, you set it up for 0, you have 0, 0, that's 5. 0, 1, that's 10. 0, 1, 0, minus 1, 1, 2, that's 2. So that's us setting that up there. So I can run this now while we get ready. So this is going to be attached to the next set of things you're going to be doing. So that's why we need to get that in place first. So this is not necessarily going to output any results, but it is a preparation. So it's run now. So it's a preparation for other things you're going to come to do later. So then we have value iteration. So we have an update through V sub k plus 1 of S equals maximum over the actions of, this expression you have right here. So this iteratively converges to the optimal value function. Okay. So, and running the first time, if I run it now, we get 27.56, 13.02. So what has happened here? You have V is NP dot zeros for I in range 10. That's from 0 to 10, I believe, or 0 to 9. So you have a new V, So the V is updated. And then for S in range 2, you have action values, which is also updated. So for A in range, so you're talking, these are steps, states, and these are actions. So you have all of that based on the formula you have here right now, because you're talking about the maximum of that. So then you keep appending like that. So you keep up iterating until you finally get a V, which is the newest V you get. And then that gives you the optimal value function V. And that comes as 27.56 and 13.02. So that's the optimal value function in that case. So next, what about extracting optimal policy then? So we have got the optimal value function. Then we want to extract the optimal policy. Once we have V star S, we have pi star S, and we take this whole expression now, and then we want to extract the optimal policy. So that means which state and which action is the best, so to speak. So, and we have policy NP zeros 2. We're talking about integers now. So for S in range 2, we have action values. For A in range 2, we have value, and we sum up all of whatever we can sum, and then we take the final policy, and then we end up with the optimal policy, which is 1, 1. That means state 1, action 1, kind of. Then we move on to policy iteration. So we have two steps here. You have the policy evaluation, which is V pi of S, which is equal to this whole expression. And you have the policy improvement, that's pi prime of S, which is argmax over a Q of S comma A. And then, we can do all of that with maths, with a Python code. So this is now, it's like this is putting together everything we've done previously. And so if we do all of that, so the optimal policy ends up being the one that we got, right? And then we then have the improved policy. That's 31 point, value function is now 31.32 and 16.77. What we got before was 27.56 and 13. So here, uh I think the 13, okay, this one is now upgraded to 16. But let me see if we keep running it, are we going to keep getting, we keep getting the same answer? So it converges to an optimal value function like that. Okay, so uh, the first time we saw value function, right? I want to see that first expression about value function to explain this one if necessary. Value function. Okay, we have action value function like this here. So for this, for the action. So you have state value function, you have action value function like that. So that's what we have right there. So that's talking about state and action in each case. Okay. So in summary, we can say then that MDP model sequential decision making, so that you're in a state to take an action, uh, and you get a kind of reward, and then you move to another state, or you remain in the same state, whatever happens. So MDP model sequential decision making, value functions estimate expected rewards. Then Bellman equations define recursive relationships, and value iteration directly finds optimal values. Policy iteration alternates evaluation and improvement. All right. And the key insight here is that optimal decisions come from maximizing expected future rewards. So you want to keep doing what gives you the maximum benefit for sure in any situation. So in 55.10 now tells us about next topics that we may want to consider after this. In fact, I think one of the videos ahead will be looking at Monte Carlo methods. Then there's temporal difference learning. That's another. Of course, that I don't have that in this series, but I mean that's if you really want to explore further the idea of Markov decision processes. So Monte Carlo methods, temporal difference learning, Q learning, deep reinforcement learning, MDPs are the foundation of reinforcement learning. I'm going to touch on reinforcement learning. I think that'll be the last video in this, as far as this playlist is concerned. So we have some practice problems in which you want to try your hands on. So I'll just flash them and round off. Um, so first of all, you have conceptual questions. Explain the Markov property. Why is it important in MDPs? So I keep saying that the Markov property tells us that the next state is determined by only the current state, and the states before now are not necessary. Okay, so it's more like saying that if you have to write it mathematically, right? Probability that if it say let's say state t plus one, the current state, given uh the previous states and the states before it, if you like, and you keep going like that. It's simply the same thing as probability s of t plus 1 given s of t, because all these other states don't matter. That's the Markov property. So the next state is only determined by the current state. Okay. So then list and describe all components of an MDP. Of course, this is state, these are the actions, these are the what are the P's now? Uh Okay, I need to quickly refresh that. That's transition probability. I should know transition probability, and then you have the reward, and of course you have the discount factor. All of this play out in a system. So what is the difference between deterministic policy and stochastic policy? Of course, the stochastic policy is probabilistic. Deterministic policy is of course deterministic, like a kind of formula thing for sure. Then explain the role of the discount factor. What happens when gamma is zero? Of course, discount factor, when it is zero, it means there's no, you're going nowhere. It's more like you're stuck there. But when it is close to one, it means there's it's serious probability of moving ahead. I mean, that's a layman's explanation I can give right now. To differentiate between state value function v pi and action value function, that you want to check that out. Mathematical derivation problems. Write the Bellman expectation equation for this. Write the Bellman optimality equation for that. So you have all those equations up there. Then show that q pi s comma a relates to v pi of s. Then prove that the Bellman operator is contraction mapping, like using the outline only. Then given that v s prime is 5 and the reward at s comma a is 2 and gamma is 0.9, you want to compute all of this. Of course, I mean, that's just straight up, straightforward. That's r of s is 2 plus gamma, that's 0.9 times 0.9 times 5, right? So 0.9 times 5 is 4.5 plus 2, that's 6.5. Then you have numerical problems like the kind of setup we had here before. So you can use that to compute this whole thing, right? And just put them together. Then questions 12 and 13 now. You have given two actions with values. This Q uh, at a particular state, the value state S with action 1 is 8, and same state S with action 2, the value is 10. So you want to find V star S. So you want to use the formula I showed before, that we saw before, to do all that. Then you have a given policy, pi A1 given S is 0.7, A2 given S is 0.3, and Q is all this. So you then want to compute V pi of S. So you use the formula that we saw for V pi of S initially. I think yeah, this is it right here, V pi of S. So it's a matter of just putting it all together. So then we have 14. If V of S1 is 4, V of S2 is 6, P is 0.5, 0.5, R1, R is 1, and gamma is 0.9. Compute one Bellman update. So you can do that. So perform one iteration of value for this. Then you have algorithmic problems like write a pseudo code for value iteration, write pseudo code for policy iteration. Like you can use the codes I already considered before. So explain the difference between policy evaluation and policy improvement. So of course, since you're looking at the optimal value, right? So you get a result and you update it to see if you can get something better, towards which it finally converges. Then why does value iteration converge? Of course, because yeah, it's designed to converge, right? Because you want to end up getting the best reward you can get. So compare value iteration, policy iteration in terms of speed, complexity, and practical use. And then we have a challenge problem here. So just like the kind of setup we had there. So this elaborate thing you want to check. You can even use the same code. So just use the same code to bring this to life. So you have a challenge problem for as a bonus. So consider a three-state MDP. So if you consider a three-state MDP, state S012, actions A01, and discount factor is 0.9. Transitions from state 0, action 0, state 1, that's 1.0. So, I mean, just like that, there you can use the code and, to do this. like that. So let me know how helpful this is for you. And if there's something else let me try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, what exactly are you waiting for? Go ahead, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join, which gives you special privileges like getting to see some videos first or seeing some videos exclusively as a member of the channel. You can also hang out with me to discuss whatever interests you on my channel or request for PDF copies of my notes and all that. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.